Hello, my name is Tom Stone. I'm the National Sales Manager of Industrial Markets for Thermal Care. Today we will be talking about benefits and designs of free cooling chiller systems. So a little bit about me. I graduated from Purdue University with a mechanical engineering degree. I have been in the process cooling industry for 14 years. I started as a sales engineer, which would help with design and application, supporting outside salespeople, as well as actually handling some direct sales as well. From that position, I moved into a project management role where it was designing large chilling systems for entire plant-wide projects, or generally just facilitating with installation, service, and construction of those systems as well. I then moved into territory sales management, where I was the regional sales manager for the East Coast of the United States. Now I've moved into this new position as the national sales manager focused on our industrial markets, which basically covers everything that's not directly related to a plastics processing. As Thermal Care, we serve over 50 different industries, and we've actually been in business for over 50 years now. So this is our 51st year. What we're going to start with today is talking about central chillers. And we need to understand what a central chiller is, what it does, and then we're also going to talk about a cooling tower and what it does and how it operates, as well as an adiabatic fluid cooler. All three of those components work together to form what we would call that free cooling design. So we first need to understand the basics a little bit before we can talk about the actual operation of free cooling. So a central chiller is in contrast to what would be known as like a portable chiller. Those are small packaged units that are typically located near the usage point, where a central chiller is a large capacity unit that's generally located in, say, a mechanical room or on a mezzanine, and it supports an entire facility or a wing of a facility, many machines, and what it actually does is has stages of unloading. It utilizes a tank and pump system that would complement it to distribute the water throughout the plant. And so what we have here is a good example of a central chiller setup. This is actually a mezzanine that's inside of the facility, but as you can see there on the top of that mezzanine, that's a central chiller. And then down below there's that large panel with all those indicator lights on that. And what that actually does is that has a process pump and then a chiller pump. And what happens is the process pump pulls water from what would be known as the cold well of that tank. It then pumps that water out to the process or whatever's generating the heat. In some cases, it could be an injection molding facility. It could be a heat treating operation, lasers, you name it. Anything that really generates heat requires some cooling. So this process pump delivers that cooling water to those usage points. It then gathers the heat and pulls that out of those pieces of equipment and brings it back. It then returns back to that same tank, which is basically it's partially divided. It's more of a thermal divide than a physical divide. And what that helps to do is to create a hot well and a cold well. So that water that's now returned from gathering the heat at the customer's processes, it then goes to that hot well of that tank. We then have a chiller pump, which pulls that hot water out and sends it to the chiller. So in this picture here, we would pump up from that ground below the mezzanine up to the chiller on top, where it will then be cooled. And that chiller uses refrigeration through a heat exchanger to remove the heat from that water. That water is now cold, leaving the chiller, and returns to the cold well of that tank. It then starts that process all over again with the process pump delivering it out. So if you can imagine it, tracking the water is almost like a figure eight, where it goes out to the process, returns to the tank, up to the chiller, and return to the tank to start over again. So there are three main types of chiller. And these could be both portable or the central large variety that we're going to be more focused on here. In this case, what we have depicted here is a packaged air-cooled unit. And because these units are such a high capacity, we're never going to really talk about the actual displacement of the heat outside of the chiller being inside of a building, because that would be too much of a heat load on the central cooling, like the HVAC system. So for capacities of large central chillers, that heat is always going to be rejected outside of the building. So in this case, the entire chiller itself is packaged out there. So that contains the fans, which are rejecting the heat ultimately to the atmosphere, but also it contains that complete refrigeration circuit. So what happens here is you can kind of see that figure 8 here. It's a little harder to see with the routing of the piping, but we have that red piping that pulls from the tank and pumps out and through that wall and then into the chiller. It then returns cool now as that blue line and returns to the other side of that tank. So that's that figure 8 we talked about. So what's happening here is it's just the water that's going in and out. And so in an instance like this, because you have that chiller sitting outside, a lot of times you'll have to account for the ambient conditions that it would be exposed to. And so in this case, we could be operating at a temperature well above freezing as the set point of the chiller, but we'll still need to include a glycol solution within that water to protect it from the ambient condition it could be exposed to. So that's one of the things you must consider here. Another style of chiller is a water-cooled chiller. And so basically what this does is it takes away that integral fan set that we depicted on that previous slide. And so what we now have is we have two water loops. One of them is the chilled water loop, which is a lower temperature. And then we have the cooling tower water loop, which is a higher temperature. And the cooling tower is used for the higher temperatures because it actually uses evaporation to achieve its cooling and the heat rejection. And because of that, it can only achieve certain temperatures. With a chiller, because we're using refrigeration, we can achieve much lower temperatures. So what we can do is we can utilize that higher temperature water to actually pull the heat out of the chiller system as well. And so what we have here is a water-cooled chiller. So there's no fans involved with that chiller. The only fan in the system is actually on that cooling tower itself, which we'll talk a little bit more about exactly how that functions. And then finally, we have a remote air-cooled. So basically what we've done is, if you can imagine that first setup with the air-cooled chiller, the packaged unit that was sitting outside, what we've actually done is we've split that into two pieces. We have the chiller with the refrigeration circuit inside of the facility. And then on the outside, we have what we would call the condenser, the remote condenser. And so that houses those fans where it uses that air to force that heat out of the system and into the atmosphere. So the only thing connecting these two items is actual refrigeration copper piping. And so what this allows you to do is you have the chiller now inside, and so that water is never being pumped outside. So you're never exposed to those ambient conditions for the water, so you could potentially avoid a glycol solution if you wanted. Then what we're still able to do is reject that heat outside of the building. And so this is a very elegant solution for taking the benefits of an air-cooled system, but also avoiding some of the downfalls of that outdoor system. Next, we'll talk about our cooling towers. So a cooling tower, it uses evaporation. And so with a cooling tower, evaporation is a very effective means of rejecting heat. It actually does a very great job of absorbing energy. And so what happens with this is we're actually going to spray water, and I'll show you a diagram here in a second of this, and we'll use air to cause partial evaporation. So what's left is a cooler water. Part of the problem with the cooling tower is that it is open to the atmosphere, and I've heard it referred to as they're like big air scrubbers. So anything that's in the air, leaves, dirt, dust, cottonwood, anything like that, that's actually going to be pulled in and can actually enter into your processed water. So if that water is now pumped out to your machines that you're using, you risk that potential contamination. You also have actual evaporation occurring. And so when you evaporate water, only the water leaves. So all the dissolved solids, everything else stays behind. So you can get very high concentrations of dissolved solids in there. So one of the things that needs to be done is water has to be chemically treated, but also you will need to consider pumping off some of that high concentration water to then be refilled with a lower concentration to maintain that level of dissolved solids in there so it doesn't hurt the operation of the system. So what we're showing here is this is on the diagram on the left there is a a cooling tower and how it would operate. And so as you can see here, what this is depicting is what's known as a counterflow cooling tower. So the hot water comes in the top there on that left with that red bar across it, and those are sprayers. And if you actually look on the right there at that photograph, that's a distribution tree or distribution piping that would be inside of a cooling tower. And those gray nozzles sticking down there are actually what use a centrifugal force. As that water is pumped through them, it spins out and then actually sprays over. And if you see that black structure there that looks kind of like a honeycomb, that's what's known as fill. And that fill creates a lot of surface area because we want to maximize our ability to evaporate, because that maximizes the capacity of the cooling tower. So by having that honeycomb structure in there, we guarantee the maximum amount of surface area available. And as long as we get a good spray pattern over that, we do a very good and effective job of getting that evaporation. So if you look over to the left again at the diagram, that's that gray bar there is what we're representing as the fill. And so the warm water is sprayed over that. Then we have a fan that's at the top of the unit. And what it actually does is it pulls in the air from the sides at the bottom and then up through the tower across that fill. And that fill is now what's covered in water. And so as we drag that water across there, we get the evaporation. And so that evaporation is what actually performs the cooling. So what water doesn't evaporate has now had energy that was pulled out of it and lowers the temperature. So it then gathers in the bottom in that collection basin as the now cool water that we'll be using. The next type of cooling for a high temperature, so not using refrigeration, is going to be an adiabatic fluid cooler. And what this actually does is it kind of combines a traditional dry fluid cooler, which would essentially just be like a radiator that's on your car. It uses forced air to cool a liquid. But what these units do is it actually uses a process called adiabatic process that basically pre-cools the air. So what we're actually doing there, if you see on that unit depicted, there's the brownish red area on the side. What that is that's actually like a medium that can be soaked in water. And so when this unit is running, and just by using forced air based on the ambient temperature, if this unit cannot achieve its set point, it will then release water sprayers at the top that will then soak that medium on the side there. And so now as the air is pulled across, it will actually pre-cool that air. And so this diagram over here will actually depict that a little more clearly. So what we're seeing here is the blue air in, that's ambient air temperature. And so if that's too warm to allow us to reach our desired set point, we can then use the adiabatic system, which is depicted there with that adiabatic cooling pad. That unit will get soaked, and as the air pulls across there, it actually pre-cools that air. So it lowers the actual temperature that is seen at the heat exchanger that is exchanging the energy from the water into the air. Ultimately, those fans then reject that now warm air out the top. One of the nice things about these units is that, one, you don't have to use evaporation all the time like a cooling tower does, because you're actually using that forced air convection over a heat exchanger to get your cooling. And then also, because you have that heat exchanger in there, it's a closed loop. So it's not open to the atmosphere like that cooling tower. So one, you're greatly reduced on the amount of treatment from a chemical standpoint that you will need. The water stays clean, and then you're also not worried about those dissolved solids because it's the same water over and over again. You're not exhausting that water supply and having to replenish it.
I look forward to sharing the in-depth review of bringing together these components in part number 2 of this webinar series to create a complete free cooling system solution. Thank you for your time, and I hope you learned something.